Hi guys, good morning. Hope you're doing well. So I want us to talk about work, power, and energy in this lesson. I hope it's not a long video. I'll try to keep it under 20 minutes. Work, power, and energy. Work, power, and energy. That's what I want us to talk about today. So you have already been introduced to some of these terms. For example, energy. In that video that you talked about yesterday, I think you were introduced to some of these terms. But the whole unit is just these three ideas: work, power, and energy. And I want us to start by talking about work. Work is simply the product of force and distance, right? Simply the product of force and displacement, right? Displacement. Force and displacement. So the work done on an object is given by the force that's acting on that object times the displacement that that object goes through. That is work done. It's very important that this is displacement, because if, for example, you run around the football field, you're using some force, obviously, or even if you push wheelbarrow around the football field, at the end of the day, when you go and come back, your displacement is zero, so you've not done any work. So it's very important that this has to be displacement. Work done on an object is force times displacement. The units for work, because force is newtons and displacement is meters, so the unit is a Newton meter, but it's called a joule in honor of some guy called Joule. I think he was a British scientist called Joule. So the units for work is a joule or joules. So if, for example, you push if you use 5 newtons to push this block, let's say this is a block that you're pushing, and you use 5 newtons to push it for 2 meters, then your work done is going to be 5 times 2, which is equal to 10 joules, right? Joules. So yeah, that is the basic definition of work done. It's force times displacement, right? And if you're wondering what 1 joule is, this is a challenge I can give you. What do you guys think 1 joule is? Because we've seen that a joule is Newton times meter, right? So if you want to find the definition for a joule, it would be the work done when a force of 1 Newton moves an object through a distance of 1 meter, right? 1 Newton moves through a distance of 1 meter, the work done is called 1 joule. Now, work is done in all sorts of situations. It's done in horizontal motion, it's done in vertical motion, it's done in motion at an angle. So we're going to look at all of those ideas. The underlying key factor is that it has to be force times displacement. Now, what would happen if this force is acting at an angle to this object? Let's say the force is acting over there, right? And the object is moving horizontally. Let's say you're pulling something with a rope, and obviously the component of force responsible for the horizontal movement is this component here, F cosine theta, if this angle is theta. So if you figure out the distance or the displacement that this object moves, then the work that is done is going to be equal to that force, that component of the force that's responsible, the component of the force that's responsible for the horizontal motion multiplied by the displacement. So with this in mind, I think it's more useful, and I hope you can see that when the angle is 180, which was the case here, when the angle at which the force is acting is just flat 180, then the cosine of 180 is 1, then the formula will just go back to FD. So it's more useful to generally write the formula for work as FD cosine theta, because in any case, if we have an angle, we just substitute the angle. If we don't have an angle, our formula stays as FD. So the work done, if the force is acting at an angle, I hope we don't forget, is FD cosine theta. Another idea that we can think about in terms of work when we're talking about the work done on an object is the graph. If I try to draw a graph of, because we know that work is equal to force times displacement, so if I try to draw a graph of force versus displacement, right? Force versus displacement, what do you think the area under this graph represents, right? This is representing a changing force, right? According to how I've drawn this graph, this force could be changing, or normally, a lot of the time, the force is a constant force, right? It's some constant force that's acting or being exerted. So I hope we can see that the area under this graph the area under this graph of a force versus displacement graph is going to be area is equal to length times width, because it looks like a rectangle, and the length is d, some d value, and the width is some f value. And I hope you can see that the area is force times displacement, which is still work done. So when you look at a graph of force versus displacement, the area under that graph is representing work, or work done. Alright, next thing I want us to talk about is kinetic energy and the work energy theorem. Right, and the key idea when we're talking about energy, because obviously energy flows from work, when work is done, energy is transferred. When you pull an object along the ground, right, you can hear sound, you can experience heat because of friction, there can be some heat. So because you're doing this work of pulling this object, and not just those two, but there's also motion, the object is in motion. So every time work is done on an object, energy is transferred, and energy is transferred in so many different types. There's so many different forms of energy. There's sound energy, there's heat energy, there is kinetic energy, which is the energy of motion, which we're going to talk about a little bit. There's potential energy. Potential energy means that an object has potential to do work, or an object is in a situation where there is potential for work to be done. An example is when you hold a cup, you hold a cup in your hand and you lift it above the ground. There is potential for that cup to do work when you let it go, right? And what that means is when you let it go, it's going to travel. When you let this cup go, it's going to fall downwards, and that falling is falling through a distance d under a force of gravity, right? So there's a force of gravity pulling it downwards, and that force pulls it through a distance d. So the idea of work is already there, and we're going to talk about this in a little bit. But what I'm trying to put across is that every time work is done, energy is transferred, and that energy can be transferred in any of these forms or so many other forms, right? So many other forms. So when work is done, energy is transferred. Now, what is this transfer of energy, or what does it look like? I hope you guys remember Newton's second law says F net is equal to ma, right? F net is equal to ma. So that means that when work is done by a net force, it gives a system energy of motion, right? Because this acceleration is representing motion, right? So when work is done on a system, it gives, when work is done by a net force, so if a net force does work, it's going to do net work. It's going to give the system energy of motion. Now, net work is defined to be the sum of all the work, done by all external forces on the object. That's why it is net work, just like net force is the sum of all external forces. So we know F net is equal to mass times acceleration, and we know that work, the net work, will be done by net force, right? Because work initially was just force times displacement, but net work is going to be work done by net force multiplied by the same displacement. But we have seen here that this net force is mass times acceleration. So that then I have mass times acceleration times d, right? I'm just making substitutions. This is still net work. I hope you remember from one of the equations of motion that v1 squared is equal to v naught squared. Is it plus? Is it plus? Yeah, plus 2 times acceleration times displacement, right? It's supposed to be displacement delta x, but since we're using d here, I'm just going to put displacement here. If I try to make acceleration the subject from this formula, my acceleration will be v1 squared minus v naught squared divided by 2d, right? So that's my acceleration. I'm going to get this acceleration and substitute it in that position. So instead of work net is equal to MAD or MAD, I'm going to have work net work is equal to mass times acceleration, but acceleration is now v1 squared minus v naught squared divided by 2d, and that is being multiplied by d. So I hope we can see that the d cancels out, this d cancels out with that d, and I'm left with m v1 squared minus v naught squared divided by 2. I can break this apart into mv1 squared divided by 2 minus mv0 squared divided by 2. That is net work. Now what you see here is that this quantity mv squared is changing. So when the network is done, or when network happens, it leads to a change in this quantity mv squared, right? mv squared changes. Network leads to a change in this quantity mv squared over 2. And this quantity mv squared over 2 is what in physics is known as, or even in science, is known as kinetic energy. And it's also known as the energy of motion. So kinetic energy is simply half times mass times velocity squared. And I hope you can see that dependence on velocity is a square relationship, or a square dependence. That means that when you increase your velocity, because we've seen that kinetic energy is half mv squared, and also obviously you don't have to memorize how to prove this, right? It will not be asked of you, but it's just showing you where it comes from. I'm just trying to show you here that the energy dependence on the speed is a square relationship. So if you increase your speed from say 10 kilometers per hour to 20 kilometers per hour, right, you would think that the energy that you have is doubling, but no, it's increasing by a square factor, right? At 10 kilometers per hour, your kinetic energy was a half times the mass of the car. Let's say the car is 1,000 kilograms times 10 kilometers per hour. You have to change that to meters per second. If you're doubling your speed, this is 10 squared. If you're doubling your speed, then your kinetic energy is a half times the same mass of the car times 20 squared, right? So this is not directly double of this. It's a 4-time factor. I hope that makes sense. If I double the speed, the energy increases by a factor of 4. So this is why it's very important to consider this, because if you're driving and you think, oh, I'm only doubling the speed, so I only have double the amount of energy, it's not true. It means your brakes have to work 4 times as hard when you drive twice as fast. Your brakes have to work 4 times as hard to get rid of all of that kinetic energy, to bring you to a stop in case you are in a situation where you have to stop immediately. So all these considerations are important to make. Now what we've seen right now is that when work is done, energy is transferred, and that energy is usually energy of motion, a half mv squared, right? That energy is usually energy of motion. Work done brings about motion. When work is done on an object, energy is transferred, which comes in as motion. Gravitational potential energy, I hinted on this a little bit earlier. Now gravitational potential energy, I'll start by trying to explain potential energy again. When an object is in a state where there is potential for work to be done, think of the cup that you are holding up and you're going to let go, or it can even be a spring. When you compress the spring, if you keep it, compressed, nothing will happen, but as soon as you let go of the spring, there's potential for that spring to extend and therefore do some work or do some damage. So if something has that kind of potential to do work, to transfer energy, anything that has that kind of potential to transfer energy, we say it has potential energy. That's what we call potential energy. That's the thinking or the idea behind potential energy. Now gravitational potential energy is work that can be done, that is likely to be done by the force of gravity. We know the force of gravity is equal to g m1 m2 divided by the distance between the objects squared, or just simply at the surface of the earth, the force of gravity is just mg. So this is the force that has potential to do work. So work done by gravity, right? Work done by gravity, or gravitational potential energy, is going to be F of gravity multiplied by distance. And we know that force of gravity is mass times gravity, mg. And the distance, usually the force of gravity works in vertical distances when the object is falling. So we're going to replace that d with height, because that distance is usually h. So work done, gravitational potential energy is given by m times g times h, which commonly is just mgh. So if I want to figure out what gravitational potential energy is, work done by the force of gravity, or sometimes it's written as gravitational potential energy, G subscript PE is just equal to mass times gravity times height, right? Obviously, when an object falls from here, and it, as it's falling, that initially it was at rest, it had gravitational potential energy, but as it's falling, this height is decreasing, and when the height is decreasing, I hope you can see here, as the height decreases, it is losing potential energy. So gravitational potential energy is one of the conservative forces because it stores energy. The energy is stored in the system, meaning that if you're holding your cup at some height above the ground, that cup will always have, let's say you're holding that cup at a height of 1 meter, and that cup is 0.5 kilograms, a very heavy cup. That cup will always have potential energy of mass times gravity times height, which is 0.5 times 9.8 times 1. That will always have that energy. So it's a conservative force. The force of gravity is a conservative force, being that that energy that is stored in the system is always going to remain there until it is transferred into something else. The only way it's going to be gotten rid of is if it's transferred into something else, but that energy is going to be there. So yeah, that's gravitational potential energy. And I was just again hinting about conservative forces. Gravitational, the force of gravity is a conservative force, and if only conservative forces act, because conservative forces, they conserve, just like it says, they conserve all of the energy of the system. None of the energy is wasted. So imagine if only conservative forces act, if all the work is done by conservative forces, then that work is going to lead to a change in, we know that work done, the net work done, is going to lead to a change in an object's kinetic energy. But if all the work is done by conservative forces, then that's also going to be a change in kinetic energy. This net work done will be work done by conservative forces. Now, considering the force of gravity as a conservative force, if it does work on an object, going back to the example of your cup, if your cup falls, right, if it falls from 1 meter to 0.8 meters, right, if this was 1 meter and this is 0.8 meters, your cup has lost some gravitational potential energy, right? As it continues to fall, it is continuing to lose potential energy. It doesn't have as much potential to do work as it did at the height of 1 meter. So conservative forces lead to a loss in potential energy, right? Lead to a loss in potential energy. So these conservative forces lead to a loss in potential energy. And in other words, I can figure out the work done by conservative force by determining how much potential energy has been lost. If I determine how much energy has been lost between these two positions, then that tells me how much work was done to get this cup from here to there. So this loss in potential energy is equal to a change in kinetic energy. Should have written this as a negative change in potential energy. Lead to a negative change in potential energy. Change in potential energy. So what we have here, if I try to take the potential energy on the one side of the equation, I'll have, if I add potential energy both sides, I'll have change in kinetic energy plus change in potential energy. What this shows us is that the total energy in a system is always conserved. How? Let's see. Change in kinetic energy is going to be kinetic energy 2 minus kinetic energy 1, or final minus initial, and change in potential energy is going to be potential energy 2 minus potential energy 1 equals 0. If I take the negative values to the other side, then I'll have kinetic energy 2 plus potential energy 2 is equal to kinetic energy 1 plus potential energy 1, or initial. That's the one, if the 1 is initial and the 2 is final. So the initial kinetic energy plus the initial potential energy is also going to be equal to the final potential energy plus the final kinetic energy. This, again, no one will ask you to prove this, but this helps us to see that if conservative forces are acting on the system, then the energy is always going to be conserved. All right, let me stop here for now. I will come back. I will